Okay, so let's start with brief recap what we did last time. So last time we covered brief history of neurosymmetry. And so that was first topic, and second topic we start talking about kind of curve counting. And in a very specific example, B2. And kind of our goal was to, okay, for the curve counting we discussed, okay, so the main question was how many rational minus zero curves B2 plus 3D minus degree. And kind of we started with some recap of what people knew from algebraic geometry. Results. So when D is 1 and 1 is just 1, with a single curve passing through 2 points, curve passing through them. So then for D equals 2, we need to count quadrics passing through 5 points. And once again, we describe the quadrics as zero locus of some polynomial of degree 2, and then we kind of carefully observe it that the number of coefficients modular over LC star rescaling actually is the same as the number of points, so it is 5 coefficients, and then kind of passing through 5 points gives us 5 linear equations, and 5 linear equations on 5 complex numbers gives us unique solution. So the situation became interesting for D equals 3, because in this situation we can have kind of generic curve has genus 1, but we want to count rational curves, genus 0 curves, so therefore we need to count degenerate curves. So we want somehow to degenerate torus, which is kind of general topology for degree 3 curve, into some kind of torus with one of the cycles shrink to a point, or equivalently you can say that it is some kind of sphere with some singular point. And then kind of we have kind of 8 linear, so totally here we have 10 coefficients modular T-style rescaling, which gives us kind of 9 independent coefficients. And we have 8 linear equations because we have 8 conditions of passing through 8 points. And then we have one additional relation on the coefficients, which kind of a condition for this genus 1 curve to be degenerate to genus 0 curve. And this condition was apparently degree 12 polynomial. So this kind of thing is was degree 12 polynomial of these coefficients. And degree 12 polynomial kind of generally has 12 solutions, so therefore this number N3 is 12. And the next number kind of D equals 4, so N4 is 620, and kind of generic degree 4 curve has genus, okay, genus of a curve of degree d minus 1, d minus 2 over 2. So substituting d equals 4 gives us the genus for degree 4 curve is 3. So therefore, to get rational curve, we need to degenerate multiple times, and that seems to be like beyond standard methods of algebraic geometry. So therefore this number n4 was first got by Savage and Manning using so-called Savage-Manning recursion, Savage-Manning formula. It's like this. So ND was expressed in terms of ND1 and ND2, where D1 plus D2 is D, and most of them are non-negative. Most of them are positive, and here we have some additional vector. So D1 squared, D2 squared. Here, binomial coefficient 3D minus 4, and D1 minus 2, and then another term D1 plus D2, and D1 4, D1 1. And to compute n4, we need to kind of plug in the number that we know, n1, n2, and n3, and if we perform this summation, we will get this next number n4, and generally these numbers, they kind of grow exponentially with t. Okay, and then kind of our goal was to kind of understand how Kontsevich and Manin got this formula, and kind of what we started to do, we started to talk about general theory of strong-bit invariance, which are essentially generalizations of intersection numbers. So we will kind of adapt the definitions by Kontsevich and Manin that given a collection of cohomology classes of X, so we define this kind of object, graph is invariant of X, and here we have kind of two labels, so that is degree of the curve, and another label is genus, I think it's an opposite of that. Degree, genus, and as before, in general, these two numbers are independent, so there is some kind of bound that genus can be higher than something, but it can be lower than some kind of bound given by a degree. And here we perform an integration over moduli space of X of degree beta, suitably compactified, or to be more precise, suitably completed by Kontsevich and Manin. And here we have kind of wedge product of some differential forms of this moduli space obtained by applying pullback evaluation maps of this representative gamma of this cohomology classes. Okay, so as this evaluation maps, they essentially do the following. So they map element of this moduli space to X, and map is the following. So we have a map. So phi is the map from our curve genus E to X. And then we have kind of location of points, or map points P1 to Pn. So they are points from kind of our curve G. And then what we can do for evaluation map alpha. So we can take our map that maps sigma g to x and just evaluate image of the point here. So that will be point in x. And given this map, we can like construct the usual pullback map or differential forms. So evaluation alpha star. So we take differential form on x. Let's take n form on x and produces the same degree form on kind of models. So having collection of forms on x, we use pullback of evaluation map to get forms on m. Then we multiply the forms on m and integrate over model. So last time we observed that for this integral to be non-zero, non-zero is kind of equivalent to the dimension of this moduli space and eta should be equal to kind of total degree of the form, and because pullback maps reverse the degree, so we can compare it with the degree of the form in x. So okay, so that's what we kind of also talked last time. So we have this formula that gives us definition of this Gromov-Fit invariance. So unfortunately, like using this formula to compute Gromov-Fit invariance in kind of complex geometry setting is kind of very hard, and usually people don't use this definition. However, given this definition, we can derive a certain nice relations. So given definition, we can derive nice relations. And it turns out,
is it possible the cohomology classes, I mean the product of all these evaluation star alpha I, the cohomology class is trivial?
yes, it is possible. So there are like some Gromov-Fit invariants that vanish despite of.
I think regardless of the dimension, but just this product is zero, even though the sum of all these degree is trivial.
Let me see. Yeah, so I think product can, okay, at least the integral can vanish. So integral vanishing means that that this product is trivial in a top cohomology class. So we will see like in a moment some examples where the degree condition is satisfied, but the integral vanishes.
What's the cohomology? I mean, what's the coefficient? I mean, for the cohomology.
So here I would work over just complex numbers. So everything is kind of over complex number.
So I think it's not if and only if is the dimension is not equal the summation of degree, then it implies integral will be there.
Yeah. So integral is not zero only if. Okay. Let's. Okay. It's a good point. So that is necessary condition for integral to be non-zero. Okay. So I think it's only if. Okay. So the integral. Okay, let's make it more precise. Integral is zero unless we have this condition. So let me. Yeah, I think that's a more careful statement. So if this condition is not satisfied, then integral is definitely zero. If this condition is satisfied, then we still can get some zero answers, and we can get some non-zero. Yeah. Thank you. Good. Okay. So given this definition, we can derive certain nice relations, and in some cases, so we can derive some nice relations, and in some cases we can even use these relations to kind of completely fix or to evaluate all from and kind of Kontsevich formula is sort of one example of such behavior that certain general relations that hold for arbitrary x applied to a special situation when x is just kind of complex surface, or okay, in this case P2, like very special complex surface, is kind of sufficient to uniquely determine like all interesting chromophyte invariants. However, these relations, they kind of still present in a general setting, but not as powerful as in the case of P2, or more general in the case of kind of complex surfaces. So this kind of Kontsevich-Manin approach kind of can be generalized to a complex surfaces, and I think your first kind of homework will be essentially to generalize this construction that I will describe for P2 to the case of another simple complex surface, which is P1 cross P1. So we will do P2 today, and P1 cross P1 will be homework exercise, so I will kind of formally post the thinking of a problem sometime later today. Just kind of appetizer that this construction is not kind of unique for P2 case, but other toric surfaces can be kind of computed in a similar way. Okay, so the relations are of the following type. So one relation is called function relation. And it works in the following way. So in all our kind of constructions, x is kind of compact, and for compact x, we have compact and kind of connected. So it means that h naught of x, okay, so in kind of coefficients with complex number, okay, but just say dimension of h naught of x is 1. So therefore, in our kind of cohomology of x, we have sort of constants. So let us kind of denote omega 0, which will be just a constant form. Let me say that it just omega 0 equals to 1. So this is element of h naught of x. So let us consider the following variants of omega naught, and here we have gamma 1 to gamma n, and let's say that n is bigger than 2. So therefore we have at least three other gammas and one omega naught. That is arbitrary x, and I think it's arbitrary degree beta, and the answer is given. So kind of the word relation refers to kind of more general setting of chromophyte invariants, like descendant chromophyte invariants, which I don't want to introduce right now, and if you have time, like towards the end of the course, we will talk about descendant chromophyte invariants. So in descendant case, so this formula is really a relation. So in a sense, there is some non-vanishing right hand side. But in a special situation when there are no descendants, So this relation is kind of extremely simple. So it just tells us that if we insert sort of constant forms and we have number of marked points like 4 or more, so then such Gromov-Fit invariant vanishes. Okay, and then there is another relation, which is now actually a relation. So it is divisor relation, and once again, let's say that n. I think in this case I can say that n is bigger. Yeah, look, n is bigger than 2 for simplicity. So, okay, so for divisor relation, we need to kind of recall some other property of x. So here we have this notion of degree beta. So beta kind of degree, which in more careful terms means the following. So we have kind of image of our sigma g. So it is some kind of curve in x, and we can ask what is the homology class of this curve in kind of second homology of x. So now, kind of here, to make integer degree, I probably need some kind of integrality property, but let you trust me that there is a way to kind of carefully describe integrality property to make this beta actually integer value. So therefore, if you have second homology of x, because x is kind of compact space, so kind of having non-trivial second homology of x kind of implies that there is zero second cohomology of x, and therefore here we will have some omega. Okay, let me call it omega capital A. So they are some, let's say, basis in this H2 of x. So if I have omega A, once again, and other insertions, degree beta on x, so then this invariant is not vanishing, but can be expressed in terms of invariant with omega A removed. So what we need to do, so beta is some kind of element of H2, so it is some cycle, and then we can integrate this element of cohomology, which we can take some representative, some differential form of degree 2, so we can integrate it over beta. We will get some number, and then we multiply this number by gamma 1 n, and with the same label g degree b. Okay, so that is second relation. Let me keep the formula until we derive it. Okay, and kind of one more useful relation, which will be, I think, the key relation for this Kontsevich-Manin recursion will be okay. Maybe we will define it a bit later. So first, let us kind of apply this puncture divisor relation and in this degree selection. Let me label them 1, 2, and 3. So let us apply these relations to see what kind of Gromov-Fit invariance we have on P2. So effects.
Excuse me.
Yep.
here omega A seems to have degree 2.
Yes.
So the left hand side, if left hand side is not 0, then the amplitude on the right hand side should be 0 because we have this restriction, right? Because some lower
okay,
degree
okay,
of
okay.
gamma.
That's a good point. So let us kind of that's a good point. So there is kind of good question. So question is how can it be?
There's a lot of
Divisor relation, that both terms in a divisor relation are generally non-zero. So let us kind of carefully apply our degree selection. So what we have here? So here we have n plus 1 mark points. So we have m, g, n plus 1, x beta. And dimension of this space is the following. So okay, so we need to integrate over beta, phi1 of x, and then we need to add like this thing, 1 minus g. And then the important part, let me kind of emphasize the important difference in red, is that we have n plus 1 marks points, because we have omega a, and we have gamma 1 all the way to gamma n. So that, and for the necessary condition for integral to be non-vanishing is that that this dimension equals to sum of the degrees. Okay, so we have some observable gamma alpha, and here once again we are looking into complex dimension. So for omega alpha, that is complex degree of omega alpha. So it is two form. So it's kind of real degree is 2, but here we kind of count in complex dimensions. So we should divide this real degree by half. That's what I roughly call complex degree of this omega a. And then so that is kind of left hand side, and for the right hand side, kind of key difference is that this n plus 1 will be replaced by n, so we removed omega alpha, and therefore it will be replaced by n, and this expression will be replaced by just sum of the degrees of gamma alpha. So we see that most of the terms are the same. So this term are the same. So all these terms, they are independent on n and observables. But here in the first case we have one additional plus 1 from degree of omega alpha, and we have one additional n plus 1 from extra mark points. So therefore, if we cancel with 1, we will get exactly the degree and dimension matching condition for n observables with omega a dimension. So, and that is kind of general property that we can insert kind of arbitrary number. So we can actually repeat this analysis and observe that we can insert arbitrary number of this omega a's, omega a1, omega a2, and so on, omega ak, and with gammas, and here we will just get the product of numbers. just the product of some numbers, gamma 1, gamma n, with the same limits. So therefore we can insert like arbitrary number of degree 2 observables into Gromov-Fit invariant, and all we have is this kind of Gromov-Fit invariant with these observables removed, but multiplied by some numbers that depends on what kind of observable and degree. Okay, so let us specialize to x equals p2. So in this situation, and 80 numbers are the following. So h0, h2, and h4. The only non-vanishing empty numbers, and all of them equal to 1. So let us kind of introduce representatives. So we have omega naught, which is just identity, constant form equal to 1 everywhere. So then for omega 2, so there are like several choices in the literature. So I think for one choice we will talk a bit more later today, is to choose omega 2 to be Fourier form. That is some natural form on projective spaces. But maybe without getting into details of construction of Fourier form, you can think of other, maybe more singular form, which is Poincare dual to a hyperplane. So inside of P2, we can impose linear equation and get a hyperplane, and kind of Poincare dual to hyperplane will also represent a second cohomology class. And similarly here, for various like reasons, let me kind of denote them label them by their kind of complex dimension or by their half dimension. So omega 0, omega 1 for Fourier studio for delta function of hyperplane, and for omega 2, once again, we can either take a square of Fourier studio form, or we can take a sort of intersection of kind of two different hyperplanes, and an intersection of two hyperplanes, h1 and h2. So they will intersect to a single point, and that will be Poincare dual of the intersection point. Or we can say that it's just a Poincare dual of some abstract point on P2. So that are kind of our cohomologies and representatives that we use. And notation, so our number n, which is number of degree d curve genus 0 passing through 3-dimensional point, is a group of fit invariants of the following form. So we take omega 2 and we insert 3d minus 1 insertion of omega 2, which are just Poincare duals of points. So for all points, they kind of represent the same cohomology class. So therefore we can just insert the same omega 2. And here, first label should be 0. So it's a rational curve. And once again, H2 is one-dimensional. So that's why our kind of degree vector is just given by single non-negative integer number. So in this and here label P2. So that is kind of expression on ND in terms of Gromov-Fit invariant. So therefore, in order to compute ND, we need to compute a Gromov-Fit invariant with kind of multiple omega 2 insertion. And once again, we can do another exercise with our degree formula. So if genus is 0, we have, say, n marked points. So we are in P2 case. So degree d. So let us perform the computation for this dimension. So this one is n. And here. Okay, so what we will have? Okay, so complex dimension of P2 is 2. So it's 2 minus 1, 2 minus 3. So it is minus 1. And here we have g naught 0, 1 minus 0. So this factor is plus minus 1. So we still have this plus n. And here we need to integrate kind of first Chen class over degree d kind of hypersurface. And in the case, so first Chen class for P2 will be 3, and here will be like this delta of the hyperplane class, and kind of integrating it over degree d hyperplane will give us 3. So therefore, for this dimension, we got the following formula. So it's 3e minus 1 plus n. So now, general Gromov-Fit invariant, it kind of has a certain number of omega 0 insertions. Let me call it n0, certain number of omega 1 insertions, let me call it n1, and certain number of omega 2 insertions, let me call it n2. So then this little n will be n0 plus n1 plus n2. So it's total number of insertions of all each of 3 times. So now here, what is the degree, total degree of this little n insertions? So this omega 0 has degree 0, so it's 0 times n0, 1 times n1, plus 2 times n2. And Gromov-Fit invariant is kind of vanishing unless we have this relation that 0 times n0, 1 times n1, plus 2 times n2 equal to 3d minus 1 plus sum of these numbers. 0 and 1. So now we can observe the following property, that if you look at n1 dependence, so here n1 comes with a factor of 1, which is kind of degree 1, which is half of a real degree. And then here we have also n1 coming with a factor 1, because n was sum of n0, n1, and n2. And kind of left hand side and right hand side have the same n1 dependence, so we can just cancel it. And indeed, this degree selection formula doesn't impose any constraints on the number of n1 insertions. So that's what we kind of already saw in kind of our previous exercise with degree formula. So now here, what we left, we can also cancel the factor of 2. So we can cancel n2 contribution for the price of replacing this 2 by 1. And we get a following formula, which I need to repeat for a while. So that n2 minus n0 is 3d minus 1. So that is kind of degree selection formula. So that is necessary condition for this invariant. Let me introduce this notation, like instead of writing omega 0 n times, I will kind of roughly use this tensor power to indicate that it's not actual power of a form, but it's insertion of this form n times. So for non-vanishing condition, that is necessary condition for this thing to be non-vanishing to 0 degree. Okay, so generally we can have arbitrary number of n1 insertions, but omega 1 insertions but omega 0 and omega 2 insertions, their number should satisfy this condition. But due to, we're not going to use any of this, so, but kind of due to puncture relation, so due to 2, we have the following story. If total n is kind of bigger than 3, so 4 or higher, so we have this property that kind of insertion of omega 0 for this number positive will give us 0 answer. So therefore, for n 4 or higher, bigger or equal to 4, only non-vanishing. Okay, all Gromov invariants except one for the following type, so omega 1 to arbitrary number insertions and omega 2 exactly 3d minus 1 insertions. All Gromov invariants vanish except these ones. So and our number nd is kind of one particular case. So nd is n1 equals 0 case. Okay, so essentially puncture relation allows us to get rid of omega 0 observables if the number of points is bigger than 3. So just let me give you a remark. So why we need like number of points bigger than 3? So if number of points equal to 3, so then we can recall from last time that we had genus 0, degree 0 Gromov invariance on arbitrary space X for 3 observables, gamma 1, gamma 2, and gamma 3 would get given by integral of x of product of gamma 1, gamma 2, and gamma 3. So in particular, in the case of P2, we can have the following situation. We can have omega 0, another insertion of omega 0, and say insertion of omega 2. That will be integral over P2 of omega 2, which equals to 1. Here, once again, genus 0, degree 0. So therefore, this n bigger than 3 is important because for n equals 3, so we have examples of 3-point function with or 3-point Gromov invariance with omega 0 insertions is non-vanishing. Okay, so let me keep this relation this time. Okay, so we used puncture relation to eliminate some of the Gromov invariants. Like eliminate means that they are for sure vanishing. So now we can further use divisor relation. So we have like this invariance. Let me say n bigger than 3. 3 minus 1 and 1 bigger than 3. So there are invariants which are not vanishing, but we can further simplify because we know how to deal with omega 1 insertions. So if I have n1 insertions of omega 1 and say 3d minus 1 insertions of omega 2, so we get 0 degree d invariant. So we can use divisor relation multiple times to get the following formula. So it's d to the power n1, and here omega 2, 3d minus 1 insertion of omega 2, genus 0, degree d, d2, and we can further simplify because that is precisely our numbers n. So therefore, all these invariants that are potentially non-vanishing, so they kind of actually would be expressed just in terms of this single collection of numbers and d's, because omega 1 insertions just multiply this number and d by a power of d. Okay, so that's why essentially conclusion from 1, 2, and 3, we observed, we derived that all chromophyte invariants except listed below vanish, and all not okay, and kind of the ones that are not vanishing. So there are two types of invariants. So one case is kind of n equals to 3 case, when we have degree 0 invariant. So we have okay, let me write all of them. So we have omega 0, omega 2, which is 1, 0, degree 0. And we can have the following, the other combination omega 1, omega 1. Because if I multiply omega 1 by itself, I get omega 2. So this thing is also 1. And for number of points bigger than 3, so we have omega 1 and insertions, omega 2, 3d minus 1 insertion, genus 0, degree d, and that is d to the power 1 and d1. So all chromophyte invariants except this one vanish, and furthermore we have like this simple invariance for n equals 3. So when it's just simple invariance equal to 1, and all kind of interesting ones, they essentially expressed in terms of n and d. Okay, so indeed, given that we can compute numbers and d, we can compute all chromophyte invariants for P2. Yes.
Why we not consider n less than 3?
So for n less than 3, so we need to kind of deal with some kind of complicated construction for this moduli space. So usually kind of to get this nice relations, we want okay. So these nice relations, they kind of can be simply they can be derived using the following property of the moduli space, that there is kind of a vibration of this moduli space of kind of curves of degree d or degree beta, genus g with n points. So it's kind of space fibered over kind of moduli space of points on Riemann circles. And kind of all these relations, they kind of mimic relations on this moduli space of curves or moduli space of complex structure. And for these spaces, we really want n bigger or equal to 3. So if g is 0, so we want n bigger or equal to 3, otherwise these spaces they are ill-defined. And here, like you see, we're mostly talking about genus 0 case, So that's why we want n bigger or equal to 3 to kind of make sense of these spaces, because usually this vibration is used to derive this formula. However, we can kind of formally define like some moduli spaces that with a number of points say below 3. However, I don't want to kind of get into this thing because it's kind of complicated and I'm not an expert in this business. But when we will get to kind of tropical moduli spaces, so tropical version of M, G, N, X, so then in the tropical version, there is a kind of simple way of extending this moduli space. So that's why, like for now, I want to impose these additional conditions that for genus 0 n is bigger than 3. But in the tropical version, we will see that for n smaller than 3, there is still kind of well-defined moduli space. So for now, kind of treat it as some kind of technical assumption. So it's not a physical assumption, but technical one to make like certain things easy. But that's kind of good point, and indeed for some applications we can like get these moduli spaces and do some computations with them for n smaller than 3. That's kind of remark, but please wait till we get to kind of tropical version of this model. Okay, so now on one hand we kind of encoded all Gromov-Fit invariants in terms of NB, and how it's going to help us to get to this recursion formula. Going to help us in the following way, that in addition to this 1, 2, and 3, we have an additional property which nowadays known as a WDVV equation for genus 0 Gromov-Fit invariant. And to formulate it, so in principle we can formulate it in terms of just this invariance, but the formula will look quite complicated. And the standard way of writing this formula is to introduce generating function. So we introduce kind of generating parameter. So we call them T alpha, and they are okay, so they are kind of coefficients in expansion. So say we have gamma, and gamma belongs to homology class of X. So if we fix basis, so then we can represent arbitrary gamma in the following way: is like summation of alpha omega alpha. So they are just expansion coefficients for an arbitrary cohomology element in terms of some basis. And that will be our generating parameter. So here we can treat this gamma 1 to gamma n as some linear combination of omega 0, omega 1, and omega 2 in the case of P2. And therefore we can express every Gromov-Fit invariant with arbitrary gammas in terms of Gromov-Fit invariants computed in this basis omega 0, omega 1, and omega 2. So now let me, yeah, I don't need this property anymore, so we can use it to, we made best use of them to simplify until it many of the Gromov invariants. So let me define f that the function of this T alpha and is defined in the following way. So here we take a summation over 1. Okay, let me kind of do the definition in P2 case. So it is kind of straightforward how to generalize it to general case. So it is function of T0, T1, and T2. And here we have summation over N0, N1, and N2. Here we have Gromov invariant with N0 omega 0 insertion, N1 omega 1 insertions, and N2 omega 2 insertions. And here, let me do it in the following way. So it is genus 0, degree d, and I will multiply degree d Gromov invariant by q to the power d. And here I perform a summation d from 0 to infinity. And to get kind of T0 dependence, we say that it's T0 to the power n0 divided by n0 factorial, T1 to the power n1 divided by n1 factorial, and T2 to the power n2 divided by n2 factorial. So we have kind of function of the four variables T0, T1, T2, and Q. So Q is kind of a way to keep track of Gromov invariance of various degrees. So we kind of here formally write down this degree d invariant and Santa-Lou d2 value. However, once again, there will be only one non-vanishing invariant where d is expressed in terms of n0, n1, and n2 by the formula that I raised, 3d minus 1. But kind of still standard way of kind of repackaging our Gromov invariant in terms of this generating function. So now, given this generating function, so Witten, Degrassi, Linde, and Linde, given some physical considerations, studying topological theories, so they actually observed that such generating functions, they satisfy the following equation. So if I take a third derivative of the generating function with respect to Ta, D, and Tc, and then I take a kind of inverse of the intersection matrix. So eta AB is just intersection matrix between omega A and omega B. And eta with upper indices is just inverse of this eta. And here we take a third derivative of f with respect to some other variables, f and t. Okay, so now we get an object with this kind of 4 free indices, so it's A, B, and FG. And the statement is that here we interchange. Okay, now I need to probably recall what we interchange. I think we interchange. B and F. Yeah, indeed, so and here we interchange Bn. So that is WDV relation for this generating function for genus 0 Gromov invariance. And this WDV equation kind of holds for arbitrary x. So for all x's. Okay, so it is some kind of system of relations because we still have like this four indices, so it's a relation between different kinds of third derivatives of f. And it turns out so that that if we use this kind of simplification for Gromov invariance on P2, so on x equals P2, we can express f in terms of and d. And the formula will be the following: T0 of Q. Okay, so what we will have? So we have a contribution from 3-point invariance, this contribution and this contribution. So we have omega naught, omega naught, omega 2, which will give us contribution in the form T0 squared T1, but because it's T0 squared, we need to divide by 2 factorial. T2, and then we have omega naught, omega 1, omega 1. So it's T1 squared T0, and once again we need to divide by a factor of 2 because it's second power of 2. And for n bigger than 3, we have what? So we have invariance with n1 insertions of sum over n1, and we have e to the power n1, t1 to the power n1, and divided by n1 factorial. And then we have a separate sum over n2, but sum over n2 we can replace by sum over degree because n2 is just 3d minus 1. So here what we will have? We have q to the power d, invariant nd, but we have omega 2 insertions, like 3d minus 1 omega 2 insertions. So it's t2 to the power 3d minus 1 divided by 3d minus 1 factorial. So now we see that actually we can further simplify this formula because we can perform a summation over n1. So the number of n1 insertions can go from 0 to infinity, and recognize this sum is nothing but e to the d t1. So that is just expansion of exponent. So therefore we can kind of replace this whole sum by e to the d t1, and that gives us sum from equals 1 to infinity. So that gives us an expression for generating function for Gromov invariance, kind of purely in terms of this numbers and e. And then kind of if we use this expansion like substitute it into WDV equation. So what we will get, so WDV equation is kind of quadratic in the derivatives of f. So that will give us some kind of quadratic relations on ND. And this quadratic relation on ND turns out to be kind of upper triangular form that we can expressed like nd roughly multiplied by something like n1 or n0 in terms of lower nds. Quadratic relation on these, and this relation is kind of this contains money recursion function. So that's kind of roughly with some details of how we can get this Kontsevich-Manin recursion, starting from kind of definition of Gromov-Fit invariance as a moduli space integral. Then we don't quite compute integral, but rather use this integral formula to derive certain relations like puncture, divisor relation, and degree selection. So in a case of P2, or more generally in a case of complex surface, so we can express all Gromov-Fit invariants in terms of this number of rational curves. All Gromov-Fit invariant genus 0 in terms of this number of rational curves passing through 3D minus 1 points. And then we plug in this ansatz for generating function into WDV equation and get a relation that allows us to solve for ND in terms of a lower ND1 and ND2. So, and your first homework exercise would be kind of repeat this procedure, but in the case of x equals P1 plus P1. So there will be like 2 degrees. So because H2 is 2-dimensional, and it will be a bit more complicated, but still you can get a recursion formula that will relate like all these numbers and AB in terms of NABs with kind of strictly lower A and lower B than you have. So that will be your homework exercise, and I think I'm over time for a break, so let us make a longer break right now. Let us make 8-minute break, and then we will proceed to kind of mirror symmetry for this computation. Yes, so sorry for going a bit over time, but I wanted to kind of conclude this derivation concept. So we will meet at 11:10 and Yeah, let me actually make one additional remark about the WP equation. That was related to some questions that I had last time, and I was very briefly kind of answering it. So last time, among the things we talked about kind of quantum homology. And the idea was the following, that kind of It is a generalization or deformation of usual cohomology ring. And the idea was that the kind of the quantum cohomology product was given by a following formula. So if I have Poincare pairing on my compact space, so if I take kind of quantum product of gamma 1, gamma 2, and pair it with gamma 3, so it is the same as computing, so it is defined as a graphic invariant with these three insertions, gamma 1, gamma 2, and gamma 3, of genus 0, arbitrary degree beta, and here we sum over this degrees. And in particular, kind of when in this sum we have beta equal to 0 term, and beta equal to 0 term is just usual kind of integral, which is essentially a kind of the usual. So that is usual product, and that is products of gamma 1 and gamma 2 paired with gamma 1, paired with gamma 2, paired with gamma 3, and then kind of few corrections to it, which kind of makes it a generalization or deformation of usual product on cohomology. And the kind of key point that the main property of a product is that it is associative product. So namely gamma 1 star gamma 2 star gamma 3. We can compute this triple product by kind of adding brackets in arbitrary locations, so we can either multiply gamma 1 and gamma 2 first, multiply it by gamma 3, or multiply gamma 2 and gamma 3 first, and multiply it by gamma 1. Okay, so, and kind of that is key property that it still remains associative product, so in this sense it is deformation of this associative product structure. So then, kind of this WDV equation, it kind of looks like also some kind of quadratic relation and associativity condition written in terms of structure constants for a product is also quadratic relation. So it looks like also some kind of associativity. And it's not only looks like associativity relation, it is indeed can be formulated as associativity relation if we introduce the following. Okay, so now in terms, instead of product, I will talk about structure constants of this product, A, B, C. So they will depend on T and Q. So you can say that this kind of structure constants of the product, structure constants on product, and once again it's product on cohomologies of X. And here we do the following thing. So previously, like structure constant for quantum cohomology product was just 3-point function of gamma A, gamma B, and gamma C, and then we have like 0 beta and summation of beta. So that was usual quantum product, and now let me do the following thing. So let me insert here kind of formal insertion of arbitrary number. Let me go big exponent of gamma alpha T alpha. So this notation literally means the following, that we have like summation over n1, n2, and so on. And here we have kind of arbitrary number insertions of omega. So omega alpha, omega 1 to the power n1, omega 2 inserted n2 times, and so on. So you kind of insert all these basis elements in cosmology classes arbitrary number of times, and then multiply it by t1 to the power n1 divided by n1 factorial, and so on. And here you kind of take a summation over all this number of insertions ranging from 0 to infinity. So formally, like given this factor like t1 to the power n1 divided by n1 factorial, I can roughly treat it as some kind of expansion of a formal exponent, but here like terms in a Taylor expansion, like term that is kind of omega alpha, omega 1 to power n1, they are treated as kind of multiple insertions rather than insertion of a power function. So that's why here I have kind of tensor, not just usual. So therefore here we can use these multiple insertions of omega alpha and kind of as a function of k alpha in order to formulate some kind of structure constants where we have fixed kind of cycle object. So let me also here put elements to basis omega A, omega B, and omega C, and kind of in the background of arbitrary insertions of other omegas weighted with powers. So then it's kind of not hard to see that this object defined by this formula is nothing but a third derivative of a structure constant with respect to TA, TB, and TC. And kind of also we can notice that once again we have special omega 0 equal to 1, and we have puncture relation which basically tells us that if I have like omega 0, some omega B, omega A, omega B insertion, and some kind of exponent with other insertions, so kind of puncture relation basically tells us that any insertion from this exponent except of a trivial insertion will make this kind of Gromov-Itten invariant with 4 or more insertions. So and puncture relation tells us that if you have this identity form insertion and we have like at least 3 other insertions, such invariants vanish. So therefore this object for any degree beta is just equal to itself without any insertion from this exponent. And in kind of cohomology ring or quantum cohomology ring, so that is the way to express a kind of intersection numbers for omega alpha and omega beta in terms of this object. And here also you can show that this object is also okay. So eta AB was defined in this way. So we just intersection numbers between omega A and omega B, or intersection metrics in cohomology. So we can formulate it in the following way: it's omega naught, omega A, omega B of to 0, degree 0. So that is kind of by definition, because this thing is just equal to omega naught of h omega a h omega b integrated over x. And in the case of kind of quantum cohomology, we want to promote this kind of three-point function. We want to kind of allow it to have arbitrary beta, and we want to weight it with q to the power beta. However, once again, I think at least, okay, let me say, for projective spaces, I think you can check the degree selection. So the degree selection for this formula, like let us look at our favorite case P2. So what was the degree selection? So we have 3D minus 1. So that is kind of dimension of a moduli space, and that's supposed to be, okay, so it's 3D minus 1 plus 3 marked points. So we have 3 marked points. And that should equal to kind of total degree of omega 0 plus degree of omega alpha plus degree of omega b. So degree of omega 0 is 0, so it's just insertion of a constant. So therefore we have a formula that 3d plus 2 is kind of sum of the degrees of omega a plus degree of omega b. So omega a and omega b, they are kind of, okay, differential forms on P2. So it means that at most degree of omega is at most 2. So kind of here we are looking at this complex degrees, so we count in complex dimensions. So at most we can have like half of a real degree equal to 2. So therefore this sum is kind of bounded from above by forms. So if I take omega a and omega b to be like 2 forms, then at most I can get 4. However, here we see that if d equals 1, so this thing for d equals 1, so this expression gives us 5. So therefore for d equals 1, we have like 2 big moduli space with 3 insertions, among which is identity insertion, to kind of solve this degree selection condition for any d which is higher than 0. So for d equals 1, this thing is already 5, and then here it's maximum 4, and it can't go any higher. And here, if we on the left hand side decrease degree, then it will be like 8 for degree 2 and so on. So therefore, on x equals P2, we see that in this sum, kind of due to degree selection, so degree selection and bound on a degree for omega a and omega b, so the only contribution is still the very same contribution from degree 0, which is equal to just intersection metric. So therefore, even if we try to kind of define a more general intersection matrix using kind of quantum product, we still get the same intersection matrix as before due to degree selection. And you can suspect that similar property holds if we add some additional insertions. Yeah. Okay. So we have this structure constants defined in terms of Gromov-Fit invariance, and they are functions of t and q. And just yes.
I don't understand in the definition of this generating function why we quotient this n1 factorial and 2 nk factorial. It seems for me you are just classify the observables by their degree.
Yeah, but that's kind of part of the thing. So here you can say that
omega A and omega 1 has the same degree. Can we write them, combine them together? Then the factorial becomes n1 plus 1 factorial, something like this.
Yeah, but when you take a derivative, you will get like so in order to get like here omega A say equal to omega 1. Like you need to take derivative with respect to t1, and that will give you some extra factor of like n1 plus 1, and you will have a cancellation of n1 plus 1 divided by n1 plus 1 factorial.
So this factorial want to mention we remember the order of something.
So like I think in kind of so I would say the origin of this n factorial is because we have like a certain number of identical observables like omega 1. So and we can't really know in which particular marked points this omega 1 observables inserted. So therefore we divide by n1 factorial. So that is kind of rough explanation, but once again it's kind of part of a definition. So you can use different definition like without factorials. Like people use all different kinds of generating functions, but this generating function with factorials, it satisfies some nice WDV equation. Some other generating function might satisfy some other nice relation. So I think for now the central point is this WDV equation, which in principle we can kind of write down as a relation between Gromov-Fit invariants. So we can expand both left hand side and right hand side in powers of figures.
I want to ask the notation for the range of beta.
Okay.
Consider H star 2x or H star. I mean the range of beta.
So it's this kind of like cone, some positive cone in second homology. So
Okay.
yes, so that's why I put like plus here. So
I thought it's number 2. Yeah.
yes. Yeah. So
It's cohomology or homology.
sorry, in homology. You're right, in a second homology. So big side.
Homology or positive.
I think there is some kind of analog of Keller cone in second homologies. That, as far as I understand. So there is some kind of way of separating second homologies into like positive part and rest of it.
Yes. You are meaning this is positive degree of homology, the homology of X at positive degrees.
Yes.
The range of beta. Okay, thanks.
Yeah. So I would say that for now it's just part of a definition, and we can kind of get rid of all these generating parameters and write down kind of more complicated combinatorial formula, which will be relation between Gromov-Fit invariants. So and that
those omega 1 are identical in the sense of cohomology.
Yes. So they are kind of same cohomology classes, but you can use like different representatives if you want, and that wouldn't change that.
Since I only understand the wedge product in the chain level, so here we're doing something like wedge product in the cohomology level.
Yes. So once again, to do wedge product, like it's kind of understood nicely if you have smooth representative, like say Fubini-Studi form. You can just take a product of Fubini-Studi with itself. But if you have like the singular representatives, as I described it before, which are Poincare dual of hyperplanes, then in order to take like a product of two such objects, you want actually to deform one hyperplane some other hyperplane from the same cohomology class, but not identical geometrically to the original hyperplane. So,
And so you mentioned product of Fubini-Studi form with itself.
yes,
It's what kind of product?
just wedge, it's usual wedge
Wedge.
product. Yeah, so wedge product of
Oh,
Fubini-Studi
wedge with itself.
is kind of
Yes.
also a nice form, which is also a smooth representative in say H4.
But on the chain level, if we
Well,
wedge.
but Fubini-Studi is like if you study with a chain and do Poincare duality, you typically get a singular form, and Fubini-Studi is not a singular form. So that's why there is no problem. So you kind of have product on the chains, but then you Poincare dualize, and then kind of smooth your form a little bit, and then if you smoothen your form, then it's possible to multiply a smoothened delta function by itself and get some non-zero number. And in a sense, like Fubini-Studi form is kind of like smoothing your delta function on chain over the whole X, like smoothing your delta function on say hyperplane, which is a singular object with support on the hyperplane. But then you kind of smoothen it out by adding like some exact pieces in a such a way that now it is kind of spherically symmetric form. So it is kind of uniformly spread over the whole P2 or whole Pn. So we will talk a bit more about Fubini-Studi forms and kind of product and cohomology in terms of Fubini-Studi representatives. I think next time.
I mean, a form wedge with itself will be zero.
No, it's only if it's form of degree 1. But if it's form of degree 2, then there is no such condition.
Even degree 1, we have dx plus dy, wedge dx plus dy.
Oh yeah, so that also no dx plus dy, wedge dx plus y is 0, so it's still 0. So
dx, dy, dx.
it's like dx dy plus dy dx, so it's still 0. So for one form,
Our form is
but
even in even dimension.
I see.
no, in any dimension, like dx plus dy squares to 0 in every dimension.
I know.
Yeah, but for a 2 form, this property doesn't hold anymore. So if you take like, I don't know, dx1, dx2 plus dx3, dx4, square with, you just get like 2 dx1, dx2, dx3, dx4. So that's why here the secret property is that I think in our discussion, like we kind of often secretly assume that X is some like complex and Schiller-Keller manifold. So all these cohomology classes, they're even dimension. So that's why there is no kind of problems with some product accidentally vanish for some simple reasons like.
So sorry, I have a question. Will we prove those punctual relation?
We haven't proven it, so I kind of like describe it. So.
Yeah. And also, will we prove that this is defined on the cohomology level? It has invariance under.
Yeah. So the original definition of Gromov-Fit invariance given as an integral of a moduli space. Yeah, so given that moduli space is suitably compactified, so we have a kind of compact manifold, so then the kind of integral of a product forms, it kind of goes down to cohomologies, because if all your forms are closed forms, then changing one closed form by d of something will make like change of the whole product by d of something, and given proper compactification of your space, the change is the integral will be trivial.
I will prove in the Manin-Kontsevich way or in the WDVV way. Will we give a proof of this relation?
Of what? Of WDV?
Of this recursion relation, because you mentioned they are equivalent, WDVV and.
Yeah, you just kind of substitute, and I don't remember. I think you want like to use a component which is like one 2 component, and something. So in order to get like Kontsevich-Manin recursion relation, you need to kind of look at a specific component here, and it will just follow. I just don't remember.
Our class introduced the proof of this theorem, or the proof of the punctual relation or the divisor relation.
Okay, so we will give a proof of puncture relation and divisor relation, but not in A model, but in a B model. So okay, so our kind of approach is that I will give like a simplest proof of puncture relation and divisor relation, and for me the simplest proof is to prove it in kind of Landau-Ginzburg model, which is formulation of a B model, and then using mirror relation, you can kind of extend that proof in a B model to proof in A model. So that will be my strategy, because the kind of general mantra of this mirror symmetry for this toric varieties, or more precisely toric Vanno varieties, is that that kind of B side of a mirror. So here we are talking about A side. The B side of a mirror is typically easier. So it's easier, straightforward, and many things can be easily proven on a B side. And I will kind of use this mantra, and instead of kind of getting into complicated details of A side, which unfortunately I'm not expert in, even kind of on a tropical level, so I can kind of illustrate some of the special cases of puncture and divisor relation, but even on the tropical side, I can't give you like a full proof. But on a B side, like I can give you a full proof starting with some definitions and conjugated with a proof of a mirror symmetry. You can kind of get a proof of A side relation. So that will be my strategy. So that's why to get like a proof of puncture divisor relation and WDVV, you need to kind of wait till the like kind of later parts of our course, when we will talk about Landau-Ginzburg side model. So that is my strategy. So the proof will be given, but not in next couple of lectures. Okay, so any more questions? So yeah, so for this structure constants, WDV equation, so using kind of inverse of the intersection matrix, we can construct a kind of structure constant with upper index A, B, E, divided by the same old good eta CE. So here summation of a C. And then WDV is kind of equivalent to the following relation A, B, E, C, E. Let me keep the indices E, F, G. Equal, so that is like multiplication of gamma A. Let me call it, and then we kind of multiply it by gamma F, and then kind of get kind of component along gamma G, and here we interchange B and F. So according to this formula, it will be C, E, F, E, C, E, B, G, and that is kind of interpreted as a coefficient in the following terms. So we first multiply gamma B. Sorry. B and F. and B, multiply it, and then we multiply it by F G. Okay, so maybe messed up with indices. Okay, give me a second. A, B, E, E, F, G. Okay, so I can't quite get it. Okay, so this kind of proper indices, that should be gamma D F, and also component along gamma G. Okay, so I think I have like some issue to correct, but I will correct it and post kind of corrected version in my lecture. Sorry for that. So couldn't quite get immediately to write the WDV in terms of associativity, but I think the statement still holds that the WDV is associativity for this structure constant C. Yeah, and this structure constant C once again. So if I set all t's to 0, then so C A B E. And if I set t to 0, that will be kind of structure constants for quantum multiplication. So essentially, kind of introducing T is kind of another sort of further deformation of a quantum multiplication, but deformation by kind of insertions of other cosmology classes. And this deformation still is associative, and that is the content of WDV equation. Okay, so that turned to be.
I think you can combine this E inverse of E to the eta of to the right hand side. I mean, it's C A F E, but on the lower index.
Maybe something like this.
Yeah, and put E on the
Yeah, but that still gives me a product of kind of B and G.
The output is F. I mean, the component is F. It's
okay. So we want to say it's like this, and
on the right hand side also I think it's ABG.
Okay, it's gamma G and output is X. Okay. Thank you. So now we follow. Yeah. Thank you for correct. So indeed it can be written as associativity for this yet another deformation of multiplication. So we once deformed it by Q to get a quantum multiplication, and then we can further deform it by T using Gromov-Fit invariance with multiple points insertions, and still preserve the associativity, and that is kind of content of WDV relation.
I think we use a degree select to prove the Q-tile.
Yeah, the pairing is kind of independent of Q.
But when target is not P2.
Yeah. So for that, I think we need this kind of Fenner condition. So we need the first Chem class to be positive. So I think as long as it is Fenner variety that C1 of X is positive, I think this argument for degree selection still works.
I think this equation is proved by string equation.
No, so for string equation deals with descendants. Like here we don't have any kind of descendants.
I don't. I mean, by that puncture relation for 3 quantum beta greater than 0, it will be 0.
Yeah, but as you see, we kind of no. So we can't use puncture relation, because puncture relation is only when the number of points is 4 and higher, like including omega naught insertion. It is in my axiomatic. So that's why in my axiomatics, unfortunately I can't use just puncture relation, and I really need to use degree selection. But I think okay, so I think it's kind of good exercise. Maybe I will include it in one of the homeworks to kind of show that as long as T1 of x is positive, then kind of you have a growth of dimension of the moduli space with degree, and this growth is kind of fast. So this left hand side growth is a degree, and the right hand side is kind of bounded by twice the dimension of x. So that is maximum dimension of omega a plus omega b, and the statement is that even for first non-trivial d, this dimension on the left hand side is kind of bigger than twice dimension of x. So I think it's kind of very easy to see for projective space. So for projective space like Pn, this will be like 2n, and here will be, instead of 3, will be, I think, n plus 1. So it's n plus 1 d plus 2, and then the right hand side is kind of the sum of the degrees is bounded by 2n. And in this case, what we see? We see that if d is 1, okay, so it's n plus 3. Okay, fair point. So yeah, so that only works for P2, because here growth is like linear in n, and here growth is potentially like 2 times n. So yeah, so I need probably some other stronger conditions to eliminate correction. Okay, yeah, good point. Yes, so yeah.
I think the key point is the proof of puncture relation is not depend on M03. It's depend on universal family. The fiber of universal family has a positive dimension. So we always have this will be 0.
For positive degree. For positive degree.
Yeah. For positive.
Okay. Yeah, maybe. Okay. So yeah. Okay. So that is some gap with my knowledge. So I apologize. Okay. So for x equals p1, yes, it holds, but even for pn, yeah, we need some stronger condition. Okay. So okay, possible puncture relation for n equals 3 is equal to yeah. Okay, so remark. Okay, thank you for your comment. Okay, now okay, so I want to get to the environment. So erase some. Okay, so let me erase all this part. We want to keep quantum cosmology, and I need to keep double giving so. Okay, so now mirror of P1 of P2 and more generally and the toric family. So it is the following thing. So this is Landau Hindenburg, and we will see that we actually need to kind of further refine Landau Ginzburg. So we will later add side to it. So for now, it's just secretly there. So just Landau Ginzburg or Landau Ginzburg Zeta model with mirror superpotential. And this mirror superpotential, let me call it X, so it depends on X. And that's what kind of carries information about X. So let me kind of, so if X equals P2, so mirror superpotential is star to the complex dimension of X. So here, I think that's what people usually call X check, mirror dual. So it's P star square. And on this P star square, let me introduce the following coordinates. So, okay, let me introduce two types of coordinates. So I can introduce coordinates Z1 and Z2. So they are coordinates on C square, and we kind of understood P star square as kind of we subtract 0 from each T and take two copies. So Z1 and Z2 are just pair of non-zero complex numbers. So then mirror superpotential is Z1 plus Z2, and here will be Q over Z1. So mirror superpotential is function of Q. So it turns out that for various reasons, it is also convenient to introduce kind of exponential coordinates on C star, because C star is some kind of cylinder, so it has circle and it has real line, and kind of usually for a circle, exponential coordinates work sometimes better than algebraic. So this exponential coordinates mirror exponential is equal to iy1 equal to iy2 plus q equal to i1 plus i2. So that is kind of example. But general statement is that mirror of toric Fano is kind of Landau Ginzburg model on C star to some power, to the power which is complex dimension of X with a mirror superpotential. And mirror superpotential, it kind of carries all of this information about X, about cohomologies of X, chromophyte invariance of X. So all this encoded in WX. So therefore, the kind of key question in a mirror symmetry is and how to here the kind of question how to compute WX for a given X. And that is the question that we're going to carefully answer in tropical mirror setting. So for now, all the superpotentials, we can say that they were obtained. So originally, WX are obtained by Hori and Waffa in their kind of famous work in 2000 using gauge linear sigma model construction for topological strings. So that was kind of quite complicated construction from physics, and unfortunately, from mathematical point of view, so that is some kind of complicated black box. Mathematically, it's a complicated black box. That kind of gives you some answer for W, and then given this W, we can verify some properties that we expect from mirror pair, and then kind of conclude that yes, this W works, and we can like prove mirror symmetry for a particular X, given this additional input from a physics black box for W of X. So people can use X, W of X, and prove it mirror something. But that still kind of leaves us so that is unsatisfactory answer, because yes, given this kind of input from a black box for W of X, it is easier to prove mirror symmetry. But what we want somehow to start with A side, which is Gromov-Fit invariance on X, and derive kind of construction on the B side together with mirror superpotential. So rather than take a pair of X and W of X and kind of verify that things computed on the left hand side and things computed on the right hand side are equal. So we want to kind of improve these mathematical proofs to kind of get a complete construction that derives Wx as kind of part of its execution. So we want, and we will later in this course derive Wx from X using kind of tropicalization. So this will be a tropicalization not quite of Hori-Vafa construction, it will be a tropicalization of some other more straightforward construction. So later in 2007, it was Frenkel and Lossev who kind of eliminated GLSM part of this construction, and they showed that there is a certain way of describing kind of topological string conatoric spaces using the deformation of kind of free model on C star to the power n. So they describe like deformation of a free model by some holomorphic operators on A side, and then the reformation of holomorphics gives us kind of Landau-Ginzburg model on kind of the same C star to the power n, but with mirror superpotential. And our kind of main approach would be tropicalization of the Frenkel and Lossev, and this tropicalization will give us kind of derivation of this mirror superpotential without any kind of complicated black boxes. So in this construction, we will have like a sequence of well-defined and carefully proven mathematical theorems that will give us W. So that is kind of our main goal for this course. But before we will get into all this derivation, let us first see how we can verify mirror symmetry, given that we use the black box and got this mirror superpotential. So let me kind of do one last application of this WGB equation before I raise it. Okay, I can write. Okay, so let us recall. So recall from our historical review of mirror symmetry that the mirror for Calabi-Yau pair was kind of had this feature that certain Hodge numbers were exchanging. So in the case of mirror for toric varieties, we kind of have the following consequence that here we have homology classes on X. So just kind of treat this thing as a kind of vector space. So we have some sequence of say data numbers which tell us dimension of this homology class. So on the right hand side, if we have mirror superpotential, then we can compute the following object. So here we can compute Jacobi ring, or let's kind of temporarily call it Jacobi quotient. So we take kind of holomorphic functions on C star to the power n. Like in this kind of algebraic coordinates. Okay, so let me first give you construction, then give. So we take holomorphic functions, and then we take a quotient by kind of gradient ideal. So this thing is gradient ideal. And this gradient ideal IW is essentially generated by partial derivatives of W with respect to V1 and with respect to Vn. So we have the W with a function of Z1 and Vn, and we compute partial derivatives and we construct an ideal generated by this n functions D1, W, Dn. And then we have the following statement. So okay, so here for mirror superpotential, it turns out that what we call this space JW. So we just quotient of some infinite dimensional space of functions by this ideal. And it turns out that dimension of this space is finite for mirror superpotentials, and furthermore, dimension of this space equal to kind of sum over Betti number space. So this space has the same dimensions as the sum of the dimensions of homologies of various degrees. So that allows us to kind of establish a relation between kind of basis here and some basis in this quotient. I think I want to call it finite, just some functions that is basis in this finite dimensional space. So then it turns out. So that is kind of homology relation that this relation kind of can be further promoted to relation between cohomology rings. So here it was a relation between just vector spaces. So cohomology like vector space level, but it actually can be promoted to cohomology relation to kind of isomorphism. So we have kind of quantum cohomology ring. So here it's not kind of usual multiplication, but quantum multiplication. So quantum cohomology ring as a ring. So it's some multiplication structure of this omega A. It's isomorphic to JW also understood as a ring, because we have like natural multiplication functions on holomorphic functions on C star to the n, and this multiplication kind of nicely commutes with the quotient. So in this quotient ring we also have multiplication of classes, and the statement of mirror symmetry is that this multiplication in the Jacobi ring is the same as multiplication in quantum cohomology. So, and to kind of establish this relation, we first need to establish relation that the vector spaces on both sides, they are also of the same dimension. So, okay, so that are statements of a mirror symmetry. So let us take mirror superpotential for P2 and kind of verify it. Okay, maybe, yeah. Let me even, as I say, I'm kind of a big fan of simplest examples, and even though kind of we talked a lot about this Gromov-Witten invariance on P2, Kontsevich-Panin relation, and P2 is probably the simplest interesting case from point of view of Gromov-Witten invariance. There is somewhat simple, which is almost trivial case, which is kind of x equals P1. So it is projective space of one less dimension. So let me first illustrate how this relation works on P1 before we will like generalize it to P2. So in this case, so mirror superpotential for P1 is just, okay, so an exponential form e to the iy plus q e to the minus iy, and an algebraic form is v plus q over d. Okay, so what are the kind of cohomologies of P1? So cohomologies of P1 is two-dimensional space. So in the vector space, it is generated by kind of constants, and top form, which is, okay, you can say volume form, or class of a point, so it's different representative, so it's delta p or some kind of Sabine study, which is volume form. So that are different representatives for this omega 1. So what is kind of quantum cohomology link? So for quantum cohomology link, we need to compute 3-point function, and it turns out that the only kind of interesting 3-point function on P1. Okay, so let me be careful. So there is like this 3-point function, which is essentially a parent between omega 1 and omega 0. So it exists at degree 0. And another 3-point function, which is like insertion of 3 omega 1s, and that is non-vanishing for degree 1, 0, degree 1, and usually for quantum cohomology we take a summation of a degree, and numerically this thing equals to q. So we will get these computations later in a tropical setting. Like for now, I just kind of secretly used it before we derived it. So that is some kind of statement that kind of given careful computation. So that will be kind of quantum cohomology structure on P1. That the only non-vanishing 3-point functions are 3-point functions where we have omega naught, and omega 1, and then 3 omega 1s. So in terms of this kind of star operation, so if I multiply, say, omega naught and omega 1 by star multiplication, this kind of quantum multiplication, we get the same answer as with usual wedge multiplication, like omega naught by omega 1 is omega 1, and kind of non-trivial part of this quantum multiplication is multiplication of omega 1 and omega 1, which gives us u times omega naught, and kind of ordinary wedge product of omega 1 and omega 1 was 0 because omega 1 was already top degree form. So wedge unit with itself goes over the allowed degree of differential form of P1. So that is kind of multiplication Okay, let me, for completeness, because quantum multiplication is not commutative, so if I multiply omega 1 by omega 0, I will get the same answer, and omega 0 multiplied by omega 0 is omega 0. So that are kind of full description of quantum multiplication. So that is H star P1 and quantum multiplication computed from this pair of chromophyton vectors. Okay, so both like omega naught equal omega naught and omega naught omega 1, they kind of follow from this line, gives us all these expressions, and this invariant gives us this. Okay, so that was kind of Gromov-Witten side or A side of the mirror relation. So what about B side? So we have this superpotential. So let us compute the corresponding Jacobi. Okay, so we have kind of holomorphic functions of C star. It is essentially like Laurent polynomials. So any polynomial of z and z minus 1 is the holomorphic function of the C star. And now what is our gradient ideal? So we compute kind of partial derivative with w, what we will get 1 minus q over z square. And the kind of up to multiplication of z is equivalent to z square minus q. So we can say that it is, because here we can multiply by z and z minus 1 in the string. So we can say that the gradient ideal is generated by z square minus q. So using this relation for z square, we can eliminate so 1. So generators 1 and z. So if we choose, okay, so kind of lemma that w is just a kind of two-dimensional vector space with a basis 1 and z. So it means that if I have any other power z to the power k, when k is not equal to 0 and 1, we can use this ideal to express it in terms of a linear combination 1 and z. So it's kind of very easy if if k is positive, so k is bigger than 1, so then all we can do, we can kind of express z to the k, like we can take away these square factors. And we can use our gradient ideal to replace these square factors by q. And that allows us every time to subtract 2 from power of k. So therefore, by the subtraction, we left with either 0 or 1.
Excuse me. What does mean of the q in the ideal shape?
So q is just a number. So just.
I should think it's some complex number.
Yeah, complex number. Just complex number.
It can be any.
Any complex number. So
non-zero because it's in C star, right?
No, the q is not necessary. Z is in C star, but q I think is just a number, and actually in this situation, at least kind of when I write it down this gradient ideal, so when I kind of took derivatives of superpotential and went from superpotential to gradient ideal, so then I can even set q to 0, and then setting Q to 0 will give me like ordinary cohomology ring instead of quantum cohomology. So unfortunately, I can't quite do it on the level of W, because on the level of W, if I set Q to 0, then I get some nonsense. But at the moment, I write down a kind of Jacobi ring as kind of motion of Z minus 1. Okay, I see your point. So if I have kind of here Z minus 1, okay, yeah, good point. Yeah, let's imagine that Q is non-zero. Yeah, sorry, yeah, you're right. So if I include Z minus 1 in this definition of ring, then quotient it by Z square will run me into trouble. So yeah, so Q is non-zero complex number. Fine. Yeah, so and I need it to be non-zero, because if I have like some negative powers, like say V to the power minus M, then I want to treat, so I want to do the following thing. So I kind of multiply by V square and divide by Q, and so that will be something like I element that is trivial, which is square minus Q divided by Q. So I say against this thing, and here I put V to the minus Q. So I really need to divide by Q to turn all these negative powers into constant or Z. Yeah. So and once again by this trick I will get like V to the minus M plus 2 divided by Q, and then I can repeat this procedure to turn any negative power into 0 or 1. So V to the minus M in this Jacobi ring will be equivalent to some negative power of Q, like roughly M over 2, negative M over 2 for power of Q, multiplied by V to the 0 or V to the third power. So that was kind of our verification that Jacobi ring is defined dimensional and generated by one. Okay, so now we can compute a kind of multiplication in this Jacobi ring. So if I multiply 1 by 1, I get 1. If I multiply 1 by Z, I get Z. So that's a kind of trivial ones. And now if I multiply Z times Z, so I will get like Z square, but Z square is kind of can be further expanded in this basis 1 and Z, and kind of modulo this gradient ideal Z square equals to Q, and therefore we get Q times 1. So and then we reproduce the same quantum multiplication as we had before. So as we had on ASA. So that would be kind of a way to verify mirror relation that the Jacobi ring gives us quantum cohomology ring for a given superpotential that we got from some physics consideration. Okay, so that was kind of consideration for P1. Yeah, I think let me kind of outline how it works for P2. Okay, so let us. Okay, so we know quantum cohomology. We know kind of Gromov-Fit invariant for P2, but for the case of 3-point functions. So yeah. Okay, so H star P2 is generated by omega 0, omega 1, and omega 2.
Excuse me. So what does it mean about the quantum?
So the morphism is a ring. So here I have like ring structure. So I have like multiplication on in some basis, and here I also have like a dual basis. So I can identify like cohomology classes here and some kind of basis in this JW. And if I multiply cohomologies using quantum multiplication, it is the same as multiplying the corresponding basis elements in this Jacobi ring.
So Q in left hand side is
Okay, so Q in the left hand side was this formal parameter that we use like when we define quantum multiplication, like say omega A, 1 to multiplied by omega B. It was this summation omega A, omega B, omega C. Here was like this degree 2. And here was summation of this. So in the quantum multiplication, we have like this kind of structure constants. They were some formal series in Q, but in kind of in a Fano case, this formal series actually terminates. So this structure constants were just some polynomials in Q. So that's kind of how Q entered kind of left hand side, and for kind of each Q here. So this thing was in a more general setting when we have higher, when dimension of H2 is bigger than 1, it was something like Q1 times beta 1 to power beta 1, Qn times beta n, where n was dimension of H2 of X. And similarly, mirror superpotential in this situation will also be kind of have this dependence on this Q1 to Qm amongst the coefficients in some kind of Taylor series, or so in some Laurent series in say with variable z.
Omega 0, I think.
Omega 0.
0 AB. There's 3 insertions in the definition of quantum.
Sorry. Here, okay, good point. Okay, that would be correct. So in this 3-point function, then we use pairing to raise the index and express answer in terms of once again omega basis. So this like 3-point function was kind of what we call CABC, and in order to get structure constant, we need to kind of raise one index to get CABE, which are structure constants of multiplication. So I kind of suppressed all these lines and wrote it into single expression. Structure constant with 3 lower indices, kind of pairing to raise one index of to the zeta.
But previously we mentioned something like in P2 case, eta is eta the same as C0?
So eta AB is kind of omega 0, omega A, omega B. So it can also be computed. So here you can write it like this, but the only term that really contributes is omega 0.
So inside the bracket is omega C.
No, it's omega C, and this C is summed with this C. So summation of E and summation of a C.
So in this case, the right hand side, Q1 to Qn will be different.
Yeah, so that will be m different complex parameters, yes, and there will be some kind of condition that they are kind of non-zero complex parameters, and these complex parameters will kind of enter as parameters into mirror superpotential in such a way that when we perform this quotient, the multiplication in Jacobi ring will also depend on these q's.
So you mean we choose different Q, we will get the same ring. The ring are the Jacobi ring are isomorphic.
Yes, yes, the ring will be isomorphic. Yes, so but that will be like family of rings with multiplication that depends on a single part. So let me kind of give you an example when we have two Q's. So just okay. So that will be possibly also part of homework exercise. I'm not sure whether it will be this week or some later week. So let's take X P1 cross P1. So in this situation, as it says, like H2 of X is two-dimensional. So the degree is actually like kind of like degree with respect to this P1 and degree with respect to other P1. So in this case, kind of quantum multiplication. So there will be two Q's, Q1 and Q2, and kind of the structure constants for quantum multiplication. A, B, C depends on Q1 and Q2. That will be given by the following summation. So it's summation of A and B. Oh, okay, sorry, let's call it D1 and D2. Not too many D1 and D2. And here will be kind of omega A, omega B, omega C, homomorphic invariant, and here kind of minus 0, and for beta we have this pair of positive integer numbers d1, non-negative integer numbers d1 and d2, and here will be like q1 to the power d1, q2 to the power d2, and kind of summation over d1 and d2, which are positive. So and yeah, let me give you some case. So let me here so the basis in H star of X. So it will be omega 0 and then there will be two omegas. Okay, so it's 2 omega 1. Yeah, okay, so let me call them omega 1, omega 2, and omega 3. So that will be H2 of X, and that will be H4 of X. That will be H0 of X. So if I multiply 2 omega 1s, I will get kind of Q1 times omega 0, and if I multiply 2 omega 2s, I get times omega 0. Yeah, and if I multiply, say, omega 3 and omega 3, I will get Q1 times Q2 times omega 0. So kind of there will be this structure constants that depends on Q. So and the mirror superpotential for P1 plus P1 you have the following form: P1 plus Q1 over P1 plus P2 plus Q2 over Z. And we will see and kind of Jacobi ring. So we can choose the following basis. So it's 1, Z1, Z2, and Z1 times Z2. So gradient ideal can be generated by the derivatives will be essentially kind of ideal generated by two relations. V1 square is Q1 and V2 square is Q2. So therefore, kind of any power, any positive power in V1 and V2 can be expressed. This power can be lowered by replacing V1 square by Q1 and V2 square by Q2, and similarly for non-zero Q1 and Q2. It's both Q1 and Q2. So for non-zero Q1 and Q2, we can also express inverse powers of Z1 and Z2, trade them by inverse powers of Q, and also turn any expression to expression with individual powers of Z1 and Z2 is either 0 or 1. And then kind of quantum multiplication, like multiplication is this Jacobi ring. Like say, if I multiply Z1 times Z1, I will get Z1 square, but due to the relation, that is the same as Q1 in Jacobi ring, or more precisely Q1 times the identity, and that is the same multiplication as we had in quantum cohomology ring for P1 cross P1. And similarly, if you multiply Z1 times Z2 by itself, we'll get second power in Z1 and second power in Z2, and we can individually replace them by Q1 and Q2 times 1, and that gives us the same as a quantum multiplication in P1 cross P1. So that is example when you have like multiple Qs. So you have like multiple Qs due to having multiple components in a degree. That H2 is higher dimensional. So you have like sequence. You have collection of integer numbers to specify the degree of the curve. So that's why you need several generating parameters, Q, or several deformation parameters of quantum cohomology. And the very same number of parameters will enter kind of the parameters of mirrors interconnection. And then you have like multiplication on the left hand side as a function of parameters, and multiplication in Jacobi ring also as a function of parameters of W. And as long as Q1 and Q2 on both sides are the same, so we get the same kind of multiplication or the same ring structure on both sides. So that was one side, and that was this side.
I have a little question.
Okay.
Why we need to use the structure shape of this torus? I think if we use CZ and we quotient this ideal, we will get the symmetry.
So the problem, okay, so for this ideal, yes, but the definition of it was so the definition was a gradient ideal for W, and W is not a polynomial function. So that's why only if we include z to the -1, we can turn kind of gradients of W into this simple polynomial ideal. So I can simplify the and so that's kind of the reason why I think many people prefer to work in this exponential coordinates, like e to the iy and e to the minus iy, because in this case there is no confusion between like polynomial and non-polynomial class. So in this case, kind of, or you can say that it just kind of ring of periodic functions in Y, periodic functions. But kind of W So for P1 is like this, and then the relation will be something of this type, so that is gradient ideal kind of generated by this relation. So exponential coordinates, there is no this extra confusion. But indeed, it is kind of a good observation that that if we talk about mirror symmetry on the level of quantum cohomology links, so there are many types of Jacobi rings that gives us the same kind of the same product structure. So I think let me one thing just as kind of remark. So quantum cohomology of P1 can be understood as kind of polynomials in W molded by relation W square minus Q. And similarly, the quantum cohomologies of P2 can also be expressed as kind of polynomials in W molded by relation W cubed minus 1. So that is kind of equivalent description of quantum cohomology, because all kind of cohomologies can be generated by powers of H2. H power 0, omega 1, and omega to the power 2. So we can kind of generate all these representatives by just taking powers of the single omega, say for Binich2. So therefore, not surprising that the quantum cohomology ring can be expressed as some sort of Jacobi ring. So that is Jacobi ring.
I think with the quantum cohomology, we should write Q in the generator for this ring.
Q in the generator. Where?
Yeah, Q is the generator for the quantum.
No, Q is parameter. No,
Q is parameter for the Jacobi ring, but it should be a generator for the.
Okay, so that strictly speaking is true, because here like omega is a two form. So when we say that omega cube equals to Q, we should treat like Q as some kind of. So Q should have some homological degree. But modular this subtlety. So like this kind of ring looks like a Jacobi ring for potential which is v to the 4 over 4 minus QD. So just Jacobi ring for x check equals C. So we take the functions on C, which are polynomials in V, and quotient it by the thing, and we get the kind of the same quantum cohomology ring as we had for P2. And indeed, that is kind of the problem if you just try to guess what's the mirror description based on purely quantum cohomology. You can get like many answers that reproduce a quantum cohomology correctly. However, this kind of expressions like this Jacobi just fake mirror with x check is C and in this quartic superpotential, so they actually wouldn't pass like more refined relations. So here there is like a stronger relation that we will talk next time, which will be a relation between Gromov-Witten invariance on kind of A side and kind of certain residue integrals computed on a B side. So and for kind of honest, correct mirror superpotential, these additional relations will hold, and for this kind of mirror relation, this additional kind of relation between Gromov-Fit invariance and residues of superpotential wouldn't hold. So that is some kind of important remark that indeed kind of quantum cohomology rings of, especially of projective spaces, they like modulo this issue of cohomological degree of Q, they suspiciously look like Jacobi rings for some polynomial potentials of a simple variable. But it turns out that to get like more interesting properties of this mirror pair, like matching of Gromov-Fit invariance, these naive mirrors they wouldn't work. And we need to use actual mirror superpotential for P2, which is kind of way more complicated. So it's Z1 plus D2 plus Q with D1 D2 and X check is X. So that is kind of actual mirror, and this one is something like making. So I think I'm getting way over time. So if people want to leave, they can leave, but they can answer some questions. Yes. So yes.
So this n, this star n, the n means the dimension of the x, or
Yes. So in this relation, yeah, I think I erased it. Yes, but in the mirror relation, yes, this complex dimension of x is n. So it's star to the complex dimension of x.
so for this mirror, Z2 means which class in P2? Is the omega square?
For which mirror? For correct or
For the correct mirror.
So for correct mirror, like I think you can show that Jacobi ring here. We can choose a basis 1, Z1, and Z1 squared. So in Jacobi ring, you can show that Z1 is equivalent to Z2. So that's why like Z1 and Z2, they're equivalent, and you can choose one to be kind of mirror dual of omega, and for omega squared, once again you can choose Z1 square or Z1 times Z2 if you want something more symmetric.
So in all cases, Z1, Z2, they are divisor class, right?
Okay, so they will have some meaning of some compactifying divisors if we give a toric description of P2 as compactification of C star by something.
But what happens if the cohomology is not generated by the divisor class? Or this mirror?
I think for toric, I think they should be generated by divisor class.
For toric.
Yeah. So I think here I'm kind of maybe I forgot to emphasize it once again. We are like this mirror in a sense of relation between quantum cohomology, Gromov-Fit invariance, and some properties of Jacobi ring is only for toric phenomenality. So if X is kind of not toric, like say hypersurface in toric, then all this construction that doesn't work.
Okay. Is there no such construction for the hypersurface in toric?
At least as far as I know, there is no such construction. At least such simple construction.
Oh.
So and that is kind of some challenging thing that we hope to approach in the future using kind of tropicalization to somehow get something similar to this construction for hypersurface. But usually in kind of hypersurface case, you kind of get on a B side some other kind of Calabi-Yau, and then you match like Gromov-Fit invariance and the periods of that Calabi-Yau. So it's not something as simple as Jacobi ring, and it's not some kind of residue formula. So this simple construct. So in this sense, that's the reason why we want to study mirror for projective spaces, because the B side is extremely easy. So there is no kind of complicated periods. Everything is essentially given in terms of Jacobi ring, and there will be like some additional recursive constructions that will allow us to compute Gromov-Fit invariance from Jacobi ring data. So that makes kind of B side extremely simple, and that's the reason why we can use it in all these examples to essentially compute A side and make some interesting statements about A side. So
excuse me, I don't understand this construction here. Why you can say you can decide such C star to call? For me,
so that is kind of part of that black box that I didn't explain. So as I say, like from some physics consideration, like physicists did some GLSM construction, did some kind of duality in two-dimensional conformals field theory, and arrived into Landau-Ginzburg model with this target space C star to the power n and this superpotential. So
it seems to be a coordinate ring of the Venetian set, which is the critical points of W. So the X check seems to be critical datas.
No, X check is just C star to the power n in this construction. So it is true that the Jacobi ring is kind of a ring of functions on critical points of W. That is true, but that is somewhat non-trivial property of this mirror superpotential. So that is kind of trivial property if we talked about polynomial W's in a polynomial ring. So then yes, you have like finitely many critical points of W, and this Jacobi ring is just kind of coordinate ring for critical points of W. So in the case of these more complicated superpotentials, I'm not sure whether it's kind of obvious property or not. At least in kind of exponential notations, that is not obvious. But probably in this kind of Laurent series notation, probably that also can be derived that this W also has like finitely many critical points, and that is the reason why you have finite rings. Yeah, but we will see in the tropical setting like how to actually see this appearance of C star to the power n from kind of A model going into some resummation in some quantum mechanics and arriving into B model with precisely this target.
I see. So, can we explain this duality as if we have assigned a function, kind of gradient function on critical sets, then we will have another intersection theorem refined as a cycle?
I don't know. Like as I say, so mirror construction, it kind of allows us to match many different things. So I'm not sure whether such interpretation is possible. Maybe yes, maybe not. At least not that I know. Okay, so if there are no
Oh,
further
I want to know if there are a similar story about the big quantum.
no big quantum problem.
Yeah, for many insertions probability invariant.
Yeah, so that's what we're going to talk next time. So yes, it is like today we talked about kind of we verified in the case of P1 and some kind of outline it in the case of P1 cross P1 that quantum cohomology ring matches with Jacobi ring. So next time I will kind of tell you how to further promote this thing to include this large quantum cohomology ring, like how to match individual Gromov-Fit invariants on X in terms of Jacobi ring data. So there is a way to actually compute Gromov-Fit invariants, yes, using this mirror superpotential data and okay, and some additional input, which is this Kyrgyz good section, which I will once again explain next time. So it will take me quite some time to get this explanation. So that's why I wanted to stop today on the level of quantum cohomology. Yeah, but here we don't need here like I think this potential W they have like critical points. So this time you know more work on
But the Venetian set of this
yes. Yes, so that was what kind of the first statement that on the left hand side we have like cohomology ring which is finite dimensional because like there are cohomologies of some like compact smooth manifolds, they are finite dimensional. That is like some well-known theorem from algebraic topology. So that's why the first check of a mirror was to be able to match like basis in cohomology into some kind of basis in Jacobi ring. And for that we need finite basis in Jacobi ring.
But this Venetian set, this is the ideal. I mean
Yes.
If we consider
Yeah, but generally like you expect you have like n equations for n variables. So gradient ideal gives you n equations and it's intersection of n hyperplanes. So unless you are in some kind of special position, the n hyperplanes in n-dimensional space intersect over a finite number of points.
So this Jacobi ring is like a ring defined over points.
Yeah, it's essentially coordinate ring of a critical points of W. So yeah, so if would W be polynomial, so that would be like obvious statement because you will have like common Venetian locus of n polynomials of n variables.
Yeah.
So now adding allowing like negative powers of z, making it into kind of polynomials of z and z minus 1, I think it's kind of less obvious, but still true for mirror superpotential.
Yeah, well, okay, now I don't know what do we mean in the B side to assign an object in the Jacobi ring. In A side we have some intersections.
Yeah, we have like multiplication Jacobi, like in Jacobi ring you have like one natural structure that you can multiply elements from Jacobi ring, modular gradient ideal. And the statement is that this very simple structure on the P side is actually this complicated quantum cohomology multiplication that we need like to compute 3-point Gromov-Fit invariants to define. So on A side that looks very complicated. But on the B side it looks almost trivial. That is some trivial structure
Yeah.
on holomorphic functions, multiply holomorphic functions, and you can multiply holomorphic functions modulo some ideal. So that is,
Yeah.
is
So the B side always simplifies A side.
so that is kind of mantra from mathematical physics, that B side should simplify things. That's kind of why physicists were originally interested in the mirror symmetry, because they wanted to compute some kind of correlation functions in some topological string, and these correlation functions on A side, they kind of simplified to compute in Gromov-Witten value. That was still huge simplification, because instead of integrals over infinite dimensional spaces, like functional integrals, you get integrals over complicated moduli spaces, but regardless of complexity, it was finite dimensional integrals. Like that is infinitely better than infinite dimensional. But still, for physicists, like computing this Gromov-Witten invariance was like very complicated business. There were not algebraic job. And then they kind of noticed that apparently like this generating function for this invariance satisfy WDV, and as you see next time, like here you also have a very natural solution to WDV constructed from this Jacobian. So if I take like three functions, phi A, phi B, and phi C, let's say that the W is just one dimensional, so we are just on system. And I take this residue integral, and here like contour that encloses like all critical points of W. So contour like far away enough. And the statement is that so we have like this numbers C, A, B, C. And once again we have to introduce eta A, which is also variant that exists in Jacobian in the very same way as we did before. It's like A, B, and here it's like constant, which is always kind of part of a basis in Jacobian. And then the statement is that this pair, eta A, B, and C, A, B, C, they satisfy associativity relation. So it is essentially associativity relation for associativity of multiplication in Jacobi ring. So that's why Jacobi ring, it kind of naturally comes with a solution to associativity relation, and that's why kind of physicists they observed that these complicated things on the left hand side, like Gromov-Witten invariance, satisfy the same equation as the simple residue integrals in Jacobi ring. So then there was natural question, maybe we can get some Jacobi ring such that the structure constants like functions of Q and say deformed by T, so we deform W, introduce some T dependence for W, such that CABC as a function of Q and T will be the same CABC as was triple derivative of generating function for Gromov-Witten invariance. So that was main idea, to map kind of complicated problem into easy problem for some unknown superpotential, and then somehow for the cases which are interesting, somehow guess this superpotential, and then just forget about A side and use this residue formula. So that is kind of reason why physicists study that. So physicists study that for the sake of simplification, and therefore in this setting, kind of historically, it was such that the B side is simple. While if you look at the mirror in math literature, like say mirror for Calabi-Yau threefold, then A and B side, they're kind of treated on equal footing, like there is no kind of apparent simplification. So because computing some periods of symplectic form is some kind of challenging task, like on Calabi-Yau threefold. It's probably as challenging as counting some curves in Calabi-Yau threefold. So there is no apparent simplification in mathematical setting. While in physical setting, there is this simplification. And for some reason, when people Michael Gross studied kind of tropical version of this mirror, they kind of missed this point. So they formally constructed some kind of integral presentation for tropical Gromov-Fit invariants, but it was like way more complicated than original tropical Gromov-Fit invariants. And they call it mirror, but I wouldn't call it mirror because for me there is an additional criteria for mirror symmetry is that the B side should simplify things. And if it doesn't simplify things, means that we should do more work in kind of rewriting B side. But we will hopefully get to that in a tropical part. But I really wanted to kind of cover sort of standard knowledge to give you some idea why tropicalization simplifies things. That without kind of going through all this kind of painful computations on A side, you can't kind of appreciate like this beauty of tropicalization, like how it makes things simpler, because if you haven't seen how hard were things before tropicalization, there is nothing in comparison.
Now W is always a polynomial function. So
no, W is always like non-polynomial function. So it will typically be something like this. So it's Laurent polynomial. It's polynomial, but Laurent polynomial. It's polynomial in Z and V minus 1.
So is it like a theory parallel to algebraic geometry, but not differential geometry?
No, here on a B side there is kind of no geometry. Like B side is just some kind of simple algebra. Like simple basic algebra. Yeah. Like Laurent ring, like rings of C star. It's probably a bit more complicated than ring of functions on C, but not that much complicated. So it's kind of theory of functions on C star to the power n.
But in the A side, the settings are like differential, like manifolds. So
I would say like strictly speaking, A side is supposed to be like symplectic side. So it's not just manifolds, but symplectic manifolds, and usually people kind of say that it's complex symplectic manifolds to kind of avoid these issues of having kind of odd dimensional cohomology. Like you saw that with odd dimensional cohomology, things became more uglier, like various orders of products and stuff. So that's why usually, unless there is some serious reason for doing this, people kind of secretly assume that A side is not just symplectic, but actually Kähler. So that's why it's kind of some properties of Kähler manifolds, and kind of on a B side you have some algebraic construction that kind of captures geometric properties of Kähler manifolds. So I saw that you kind of when I signed up for this course on Friday. So how was it? You attended it?
Yeah.
It was like cluster algebras and BV. What was it?
Factorization.
Right? Sorry, factorization.
It's very nice. It's mathematically very rigorous. So
Okay, good.
Yeah, using some homology theory to define the two-point function.
Okay.
To introduce those to avoid those ill-defined path integral, but introduce some algebraic meaning of those path integrals. Such path integrals just want to satisfy some property, so they substitute it by some super Castillo-Gowidian formalism of.
Okay. So we will talk more about it after you take a course. Okay.
And this semester I will be free on Tuesday and Wednesday afternoon.
Okay. So I plan to talk to Andrei about our kind of meeting arrangements. So I actually still haven't finished my grant. I got like some extra special extension from Hudan, so I can still kind of polish it before March 13. So March 13 is kind of very final deadline. So that's why I'm not sure about meetings on this week, because I think this week is the last week when Andrei's students are visiting, and I think they're given talks like today and tomorrow, and kind of I think they ask Andrei to kind of help them with this kind of talks preparation. So I'm not sure about meetings this week because I'm finishing grant and Andrei is kind of still a bit busy with students, but starting next week we will have regular meetings. So and this week I hope to talk to Andrei today, and we will kind of set times for regular meetings. So and we will kind of.
These days I'm learning the Morse-bot
Okay. Okay.
There is a paper called 3 Approaches to the Morse-bot case. So I was also sending it to you. That's the one I find which covers.
Yeah, but we not only need homology, we kind of. So what you should keep in mind that what we really want, we want to kind of generalization of this refined Morse theory and quadratic relation in a Morse-bot case. So that's what we kind of ultimate goal is not just study for sake of studying, but trying to kind of study things to keep in mind that we want somehow to turn this understanding of Morse-bot theory into either guessing or better proving some kind of quadratic relation. So that is kind of our ultimate goal of studying Morse-bot.
One way to generalize to Morse-bot case is they have a so-called moduli space of cascade, which is a generalization of moduli space of gradient trajectories. It's like if you have some critical submanifold.
No, I know what cascade is, but
there will be something like this.
Yeah, but that I think is kind of introducing some kind of Morse functions on some manifolds to kind of to connect these flows between some manifolds into kind of single trajectory. I'm not sure it is true that maybe this kind of cascading trajectory can serve as some kind of regularization of Morse-bot answer, like of embedding like Morse-bot answers into Morse answers, but still, as I say, like ultimate goal is to get quadratic relation. And the way you
this
get
kind of moduli space will have boundary stratification will lead to quadratic relation. So
but like if
I suspect maybe the integral of this kind of moduli space will give us.
But with quadratic relation we kind of have some expectations based on expectations for the answer for WDVV equation. Is that we somehow, instead of summation just over critical points, we have some kind of summation over homology classes of critical submanifolds with some kind of inverse intersection metric. So if this cascading can give us the desired answer, that is great. We can declare that cascading is a way to regularize like kind of quantum mechanics in a Morse-bot case. We just regularize it by putting like epsilon times some choice of a Morse functions on these submanifolds, and the dependence on this function is kind of very weak, and essentially it gives us like summation over homologies. So as long as we can get this, that is perfectly fine. But kind of we need like to get the quadratic relation that we desire, because then we want to declare that this quadratic relation is kind of universal in the Morse-bot case, and regardless whether our Morse function is in infinite dimensional space, the structure of quadratic relation stays the same, so we can use it from finite dimensional situation. So but that would be fine. As I say, I don't have any kind of specific way of thinking about Morse-bot case, as long as a particular way of thinking gives us the quadratic relation in a form that we expect, I would be happy. So
previously when we talk about like Brown-Austin formalism, they have also a dual formulated by Fukaya, like you can substitute those de Rham chain to be singular chain. You will also get a bicomplex. This is a second approach, and this approach of cascade is a third approach. So
but there is also this idea by Andrei. So that if you do like homotopy transfer, then we kind of automatically get quadratic relation. So that was supposed to be like the most direct way of getting quadratic relation is to say that now instead of going from differential forms to kind of forms on a critical submanifolds, like that is kind of contraction that we got when we go from the Rham complex to a Morse complex. So we kind of do a contraction to a Morse Bode complex. So then the answer would satisfy quadratic relation. So the problem with this approach is to kind of justify that the terms in a homotopy transfer indeed have like some interpretation as an intersection number. So that is disadvantage of this approach. So you either start with intersection numbers and then you need like to prove that the generating function satisfies quadratic relation, or you start with some differential deformed by T alpha delta of C alpha, do a homotopy transfer, and get some kind of induced differential that automatically satisfies quadratic relation. But it's not clear whether terms in this differential they have any kind of geometric or enumerative meaning. So that essentially like two approaches that we can take. And that's what Andrei suggested, I think, before the break, was to kind of try to think about like ordinary homotopy transfer without deforming differential, like kind of understand how homotopy transfer works if you contract like the Rham differential, like reduce it to kind of to complex on Morse Bode submanifolds. So and then if we understand that part, and in that part we also hope for some geometric answer that kind of certain terms in this homotopy transfer formula that they will have something to do with this kind of integrals of forms, like push back, push forward integrals of forms over moduli space of trajectories between critical submanifolds. So that's what Andrei suggested. I suggest you to try to also think in that direction, because that kind of solving a bit inverse problem that we kind of have quadratic relation, but we want to take interpretation of terms in this quadratic relation as some kind of intersection. Okay, so yeah, I only have actually only two. Do you by chance know like what are the conditions for having ATA for a course? Do you need like 2 students sign it or 1 student sign it?
Oh. Last semester, there are 3 students registered for Mauritius course.
No. For my course, I think there was like officially 2 students registered, and I still managed to kind of get team to be paid as a TF by CMIS. So that's kind of a problem that I really want to kind of pay one of you as a TF, but the problem is that both you and Louis are the only 2 people who registered for this course. And I think if I ask one of you to be a TF, I think then I think by kind of Fudan rules, you need to kind of unregister for a course, because TF can't be teaching assistant can't be officially enrolled for a course, because it will give.
I'm okay.
Yeah. So
maybe I can contact Luis whether he wants.
So because I think both of us need TAs like me and Andrei. So let me kind of discuss with him like how we want to arrange TAs. But we also need to double check with the graduate school if one of you kind of unregistered and became TF, is it still okay? If you have like 1 official student and kind of some number of people who attended unofficially to kind of still have a TF. So maybe I'll try to. So do you know like what is the deadline for changing the courses? If you still have like
Up to this weekend.
up to this weekend.
Yeah.
Okay. So that's why me and Andrei really need to decide on TFs like by the end of this week. So if needed, you and Louis can kind of unregister for some courses.
We can unregister until
And
Sunday.
Okay,
Yes.
okay. So then we will.
But we can only register for a new course until Friday.
Okay, no, but in that situation where, but first you need to kind of check with CIMIS because before you unregister, CIMIS need to confirm that. Okay, so I need to go. So I will contact you about.
Сейчас, я не стал разговаривать, поэтому можно. Конечно, уже время. Видел, что?
Уже сейчас
Сейчас, а там очень вкусно было.
Ладно,
Сейчас 15, может быть, еще будет.
я очень